So it's my pleasure today to introduce Dr. Peter Driscoll from Carnegie Institute of Science. Peter did his bachelor degree at Dickinson College in physics and astronomy. Then he went on to do a master's at San Francisco State and another master's at Johns Hopkins. And then he finished up with his PhD at Johns Hopkins in 2010. After that is where our paths collided at Yale as postdocs in the same sort of postdoc fellowship. The last of the institutional postdocs at Yale before the department disbanded it. Maybe we did something wrong. And then Peter went on to do another position at the University of Washington for a little while. And 2 years ago, he got to Carnegie? Or a year ago? 2.5 years ago, time flies. He got to Carnegie and is now one of the geophysicists and geodynamicists there at the Department of Terrestrial Magnetism. So I thought when Ging originally had identified our sort of theme for this semester of tectonics and Earth evolution, I thought Peter would be a really great person to come and speak to us because Peter's research is by nature very theoretical, but what it does is combines observations from the core, the mantle, the crust, and the atmosphere into sort of a global perspective on how all of these different spheres in the Earth interact with one another and can give us clues about thermal histories of planetary bodies. And so that is a lot of what Peter's going to talk to you about today with his talk on inner core nucleation, which is a very hot topic. Thanks, Peter. No pun intended.
We need to turn that one light up.
I can try. Carry on.
There's no really important pictures that I can tell. A lot of cartoons.
Is that better? Oh, well, that's
We're going to go to sleep.
great. That's not happening. Does not appear so. Let's see if that.
No in between.
Setting Okay.
Okay, so thank you for the nice introduction. Thank you for inviting me here. It's been great meeting with folks already. I've never been here, so it's been interesting. I'm at the Department of Terrestrial Magnetism, as Jill said, which was founded in 1902 to study the Earth's magnetic field, but then sort of abandoned it, retained the name, and now haven't studied magnetism in 70 maybe years. I came back, so I like to say I'm bringing magnetism back to the Department of Terrestrial Magnetism, which my colleagues don't like to hear, but I like to say the joke anyway. So what I'm talking about today in particular is sort of a hot topic, actually, is when did the inner core nucleate, which is the solid innermost part of the Earth, and is there any signature of it? And people have ideas that span the entire, basically, range of possibilities. That's a very difficult problem to do, but it is very interdisciplinary, as you'll see very, very end, assuming I get there. Okay, so first, I just want to give a very quick prelude to where we're going to be thinking during this talk. So the Earth structure, as we know, has a solid mantle, a liquid outer core, which is the home of the geodynamo, which is mainly iron and some light elements, then a solid inner core, which is almost entirely iron with a tiny bit of light elements. And we know that this structure exists from seismology. So we know that the outer core is liquid and the inner core is solid, primarily from the shear wave velocity going to basically zero in the outer core. The outer core liquids cannot sustain shear waves, so this is likely what's going on. There's also a density jump at the outer core, inner core boundary for the ICB, which is used to sort of put some constraints on the composition of the core. But we don't know sort of when the inner core nucleated, and we don't know how long it's been growing and how fast it's been growing, things like that. So that's what we're going to try and get at. There are two possible scenarios for inner core formation that I can think of. One end member is that the inner core, solid part of the core, is actually inherited during formation. This is the so-called primordial theory, that somehow during the violence of formation of the planet, some bit of solid iron is actually preserved inside of the Earth. You have to invoke a number of things that namely cold accretion initially of iron bodies, but impact heating from impacts was restricted to the top of the planet, the upper mantle and crust, which I'm illustrating here, where you see as much of radius, the entropy gain or the energy deposited as a function of mass is primarily towards the outer radius of the planet. So this is from a bunch of giant impact simulations. And this is what people find. They tend to deposit most of the energy at the top of the planet. This doesn't say anything, of course, about what the interior thermal state is at the time. Okay, we're just saying where the energy is deposited. Impactor cores will, if they sink into the planet, into the core, could be hot and then could stay stratified at the top of the outer core. So that's one way to prevent mixing into the core from the impactors. And there's an even newer paper proposing that to actually solidify the liquid iron, you have to cool the core way down and overcome this nucleation barrier, which may render it implausible to actually to cool the core down that far. So the second is the more classical view. It's that it's a secondary solid, that it's solidified at some point after formation. Initially, the core, when separated from the mantle, is entirely liquid, and then at some point, the inner core nucleated at the center of the Earth, and then grew from the bottom out slowly. That's going today. And this classical view has a lot of evidence. Maybe the simplest theoretical calculation is if you balance the heat from accretion, mCp delta T basically, to the gravitational energy associated with creating the Earth, then you get an equation that tells you how much, what the temperature increase would be if you accreted the Earth at, up to some radius. So when you get up to 1 full Earth radius, there's something like 40,000 Kelvin to play with of energy deposition here. So for this primordial theory, you have to argue that this energy was all deposited near the surface and none of it went to heat in the interior. The interior stayed full all the time. And then there's additional heat from differentiation. Every time you have impacts, you have some dissipated heat, remelting of the impactors, and then inner core nucleation sometime later, question mark. Okay, so where am I going with this? I want to answer these questions in my talk here. When is our best guess for inner core nucleation? Is there any evidence for what my best guess is going to be? And what was going on the Earth's surface at the time? What are the implications? Sort of addressing what Jill was mentioning in the introduction about there being connections to the interior surface. But I'm just going to point out some possible very tenuous implications, nothing very...
When you say surface, do you include the mantle or are you just saying surface?
I mean the surface.
Surface, okay.
Yeah, we can talk about climate a little bit.
Very good.
So here's the outline of the talk. It's a little bit out of order, but I'm going to go through the thermal histories calculations, which are really the starting stage for the cooling of the Earth. This is sort of how the cooling of the Earth is computed, and it gives us an estimate of the inner core age just from a simple model. And then I will go through some magnetic observations in some detail, leading up to some numerical calculations of what the Earth's magnetic field is doing when the inner core nucleated. And this is the signature I'm looking for, the paleomagnetic signature. So we expect the magnetic field to respond in some way when the inner core first nucleates. And that signal is predicted to be very strong and obvious. We don't see it. So I'm going to go into a bit more detail into these numerical dynamos to show you what signatures they predict, which is somewhat new and unique. And then I'll go into some of the implications for the ancient dynamo itself, some paleogeography at the time, supercontinents and so forth, and some of the surface, climate, Snowball Earth possible scenarios. Okay, so part one is on the thermal histories. So we know the Earth is cooling, and we have estimates from global compilations of surface heat flux. You're seeing that from out here, where most of the heat's coming out through the ridge, where there's a thin thermal boundary layer, and then very little heat's coming through the cold, thick continental crust. And the total estimated heat flow is about 46 terawatts, teras to the 12. And I'll break down in the next slide the heat budget by sort of radial shells. And about 1 of these terawatts is by eruptive cooling. I'm just throwing that out there because that's sort of a new estimate that people have been including in the heat loss budget. And as you look back in time, we have ways to infer maybe what the mantle temperature was, even though we don't have samples directly from the core. We do know something about what's going on in the mantle from Claude Hertzberg's work and others to use the melt composition of these ancient basalts to infer sort of a geothermometer what the mantle, the ambient mantle temperature was. And they look something like this. There's some agreement on the last 2 billion years, 2.5 billion years, and then there's some scatter and some ambiguity as to what's going on before that. But I'm going to focus really on the last 2 billion models. So the evidence is strong that it's been cooling at a pretty reasonable rate between 11 and 18 terawatts of secular mantle cooling over the last 2 billion years. Okay, so our starting point is the present day heat budget before I get into the thermal history model itself. So the total surface heat flux, as I just mentioned, is 46 terawatts as measured at the surface. This is broken down between oceanic and continental heat loss. Most of the heat is lost through the ocean, the seafloor, where the crust, the thermal boundary layer is very thin. And then there's an estimated 8 terawatts of radiogenic decay going on in the continents themselves. Okay, and this radiogenic decay in the continents is not participating in mantle convection, so it's not going to contribute to my thermal history model. So I'm going to pull it out of the heat budget, and I'm left with just 38 terawatts coming out of convective mantle. And that 38 terawatts includes all the heat coming up through the rest of the planet, the core, inner core, everything. So breaking down this 38 terawatts into its components, mantle and core components, is now where the challenge comes in. And I'm putting question marks on all the rest of these numbers because they're not well known. They're not as well known. Okay. Secular cooling rate of the mantle of 13 terawatts is reasonable. It's sort of between those two scales I just showed you in the petrological evolution. Radiogenic heat loss from the mantle is also uncertain. It's 13 plus or minus 5 based on the metrology, petrological measurements. And now we have geoneutrino measurements that are falling in this range. Some argue for more, some argue for less. And then how much heat is coming out of the core, we have even less constraints on. What we know is we have to power Dynamo. So I'm going to get into the energetics of the core. We need enough heat to be coming out of the core to keep the liquid iron moving and generating a magnetic field almost as far back as we have a rock record. Okay? So that's a very strong constraint in the energetics of the core. And then breaking down the core energy budget is not terribly important, but about 7 terawatts of secular cooling in the core. I'm invoking a significant amount of radiogenic heat generated in the core, which I'm going to come back to a couple more times. And then a little bit of heat is released as the inner core itself is solidifying with latent gravitational energy. And this gives you mantle cooling rate, core cooling rate, this Urey ratio of about a third, which is sort of a good way of knowing what's the radiogenic content of the Earth. So 13 over 39 or 30 is about a third. It's just sort of a rough estimate people like to use. So now how do I take this energy budget and then compute these heat fluxes back in time, which is what I want to do, so I can make predictions about what the magnetic field is going to do at the time. So the first thing to do is to generate a temperature profile geotherm for the present day. So we have a couple anchor points here. We know where mantle melts are generated. We know that's about 1650 Kelvin or so. We know that we think we know that the inner core boundary, where the liquid adiabat from the outer core intersects the iron liquidus, is around 500 Kelvin plus or minus 100 Kelvin. And that's a very strong constraint in space. We know the exact radius of the inner core. We don't know the liquidus and the adiabat all that well. So that is still a very active area of research. And then you want to stitch together these anchor points with an adiabat in the core, a thermal boundary layer at the base of the mantle and the top of the mantle, and a well-mixed adiabatic mantle. And you want to meet the constraints that I've just mentioned. Okay. So the surface heat flow today is 20 to 39 terawatts, mantle temperature, inner core radius, and you want to maintain a dynamo. And I should say that the heat flows through the boundary layers of the mantle are computed using a parametric form for heat loss as a function of mantle temperature, which is also a whole lot of physics that I'm simplifying here, which I will touch on in a few slides. Okay, so you can do these calculations. People have been doing them for decades. They're good on your laptop or your phone probably. It's very cheap and easy. It's a 1D model with couple differential equations, one for the mantle, one for the core. And people quickly realized that you run into a problem with the temperature in the mantle. And so if you take the present day heat flows and temperatures, parameterized physics, and you go backwards in time, so you integrate your equations backward in time, then the mantle will heat up as you expect to go back in time. But at some point, the heat flow starts to get so high that the temperature one step back in time jumps catastrophically high. And this occurs, and at some point you just get this catastrophe where the temperature just becomes basically, well above the melting curve. In the very recent past, it's just entirely impossible. We have lots of well-preserved rocks going way back. So this is termed the thermal catastrophe in the last few years. There are at least two families of solutions to this problem. There's a geochemical solution, and that is to increase the mantle-Uri ratio from a third to something about twice that. Remember, the Uri ratio is radioactivity to the surface heat flow. We can't change the surface heat flow, but we don't know the radioactive number. So we're really playing with the radioactivity of the mantle at that point. So that's a big stretch. So the pro is that it solves the catastrophe. It gives you a much more reasonable temperature history. The con is that it's not geochemically supported from mantle rocks. We don't see that much radioactivity. In fact, we see probably a little bit less than this one third. The second solution is a bit more recent, is a dynamical one. And it says that heat loss, or Q, as I'm writing it here, is weakly or inversely dependent on mantle temperature itself. So you expect the hotter the fluid, the faster it's going to convect, the faster it's going to lose heat into space. So heat flow goes like mantle temperature to some positive power. So beta, in the classical model, beta is 1/3. Okay, I'm not going to explain where the 1/3 comes from, but that's just thermal boundary layer theory gives you 1/3. So this heat flow to go at temperature to the 4/3. But more recently, people have been proposing this beta factor could be 0, so or much lower. Maybe there's T to the 0. There's the codependence of the heat flow and temperature, which is a very extreme case. So the pro in this case is that it again solves the catastrophe. The con is that you're invoking these sort of new exotic dynamics that are a bit new and you don't know that much about. Okay, there's another problem, and that is the new core paradox. The second paradox, second of two paradoxes. This one's very recent. In the last 5 or 6 years, there have been a number of high pressure and high temperature measurements of the thermal conductivity of liquid iron. And these haven't really been done very carefully before. And all of these new experiments, there's maybe 5 or 10 of these experiments now, they all find that the conductivity of iron is a factor of 2 to 3 higher than previously thought, which maybe doesn't sound like much, factor 2 to 3. But that means that's putting a massive strain on the energy budget of the core. Okay, and I'll show you what that means in the next slide. Common estimates of CMP heat flow of 10 terawatts would then be below heat flow, you need to keep the core well mixed, which would, in this case, be about 15 terawatts. So if the heat flow is below the adiabatic heat flow, that means the core must be thermally stratified. That means you're not keeping the core fluid well mixed every minute. It's stratified, which is bad because we don't see that in the magnetic field measurements. Okay, so there's something weird there. Of course, the inner core we think is growing today, and as it grows, it releases chemical buoyancy and thermal buoyancy up to the bottom up through the core, which is also driving convection. Okay, so you also have that today. So maybe the problem's not so bad today because we can rely on the inner core growth. But if you go back before the inner core existed, then how was the dynamo alive? And like I said, the dynamo we know is a couple billion years old. The oldest estimates are like 4.4 billion years old if you use Earth data. So here's an example of this new core paradox. So here are some temperature histories of the mantle CMB and core over the last 4.5 million years of Earth history. And here's an estimate of the magnetic moment in black and inner core radius blue here. And you get this thermal dynamo initially for the first billion years, and then it dies because the core conductive heat flux goes to zero. There's not enough cooling to keep the core well mixed. And then after the inner core nucleates, it brings back the magnetic field eventually. But this is not consistent with the magnetic record. This is a no-go. This is a paradox. Okay? This is bad. So it's these new measurements of iron conductivity that have brought up this second paradox. It's called the Nuclear paradox. We proposed a single solution to these two paradoxes somewhat by accident. Here are the possible ways of getting out of these paradoxes. I've already mentioned a number of these. You can vary a heat source. So, for example, put radioactivity in the core, in a basemagnetic ocean, in heat double prime somewhere in the bottom of the mantle, hide it in a reservoir. You can invoke rapid and continuous exsolution, which is a very new idea. That this is an idea that as the core cools, the magnesium and silicon and oxygen become unstable and it's going to dissolve out of the iron. And that exsolution process actually drives buoyancy because as those elements leave, they leave behind a cold, dense iron which wants to sink and drive convection. But that's only a convective process, and you still need to invoke some heat to solve the thermal catastrophe. So that alone will not solve those problems unless you invoke a ton of exsolution. That's way more than what people are currently invoking. And I already mentioned the inefficient mantle cooling changing the beta factor or invoking high mantle radioactivity. So here's an illustration of what I'm talking about here. Here I'm contouring in black. There's no mantle catastrophe. There's no thermal catastrophe. And in red means it's a very recent thermal catastrophe. And on the y-axis is the Urey ratio, or how much radioactivity there is, nominal values with Earth. And then on the x-axis is this beta cooling factor, the relationship to the control of the temperature. So if you stick the Earth at the classical values of 1/3 and 1/3 for both numbers, you find there's a thermal catastrophe. Okay, I just put that out, as we know. Now, if you make one big adjustment to the heat budget, you avoid this catastrophe. So the second plot here, I'm adjusting the CMB heat flow from 8 terawatts in this case to 15 terawatts here. And what that does is I have to move this 7 terawatts from somewhere, and I'm going to take it out of the mantle cooling rate, which I can do because the mantle cooling rate is sort of uncertain between 18 and 11. Both of these are kind of reasonably consistent with the metrologic record. But this 7 terawatts in the core now is a lot. So the core cannot be cooling at this rate. So I need to invoke a bunch of radioactivity to avoid the core from past. Okay. So that's where this 3 terawatts of radioactivity, either in the core or the base of the mantle, are working really well. And you push down this catastrophe boundary down to reasonable levels, and you find there is no catastrophe under these assumptions. Just changing the heat budget does this to the extreme. This is that solution, this solution here, at that point, those parameters, time. So you can see that the mantle temperature is sort of decaying monotonically, more or less the same with the CMB and the core itself. These are the heat flows I get out of the model. And this is a prediction for the magnetic moment, this black line here, and then inner core nucleation here on this red line here. So let me first point out that this keeps the core thermally convective for all of Earth's history. This black curve is the core convective heat flux. It's always positive. This model has a core that's convecting for all time. And it implies that the inner core nucleated about 650 million years ago, plus or minus 100 million years or something. Big uncertainties there, of course. But I'm also plotting here is the next component in the story is the paleointensity data, which we're going to look at again, these gray circles. And this prediction for the magnetic moment, which comes from the core cooling rate in this plot, you can see it follows this black curve almost exactly. Doesn't seem to agree, really, with the paleointensity data at all. And I'll show this again in more detail. But, so there's a new problem now. So I've sort of solved two previous problems and introduced maybe a new, it's not a problem, it's just an inconsistency we're going to look at more carefully. Okay, so now let's look at a little bit of magnetic observations. So, when a rock with some magnetic minerals cools in the presence of an ambient magnetic field, it can preserve that ambient field if it's a strong enough field. And if that rock is then preserved somewhere on the surface that's not metamorphosed or baked or hit by lightning, you can go back and recover it, take it to the lab, and reconstruct both what the field was at the time, the intensity, the direction, ideally, but also maybe where that continent was on the surface of the Earth, if you knew what the field looked like, or if you assumed the field was something. So this is what people do. This is the game people play. For plate reconstructions going back in time. Of course, with the seafloor record, you can see the magnetic stripes on either side of the ridge, and you can rewind the tape basically to see where the continents were the last 100 million, 180 million years or something. And all of these processes are being generated by the core. So we have lots of ways of looking at sort of proxies for core dynamics back in time. And these proxies have implications over a lot of geophysical, geological processes going on there. Plate motions, plate latitudes, heat flows, and so forth. So there's two main probes that I'm going to focus on here for looking at the evolution of the magnetic field. One is magnetic field intensity, or paleointensity. This is just the strength of the field, measured in some global reference frame known as a dipole moment, which has these funny units of 10 to the typically 10 to the 21 or 10 to the 22 per meter squared. So on this scale, you're looking at virtual axial dipole moment for the last 2 million years. The present value is about 7 on this scale. So it's fluctuating. It looks random. It's just going to be more or less just random fluctuations. And if you zoom in here, you still see sort of random fluctuations in time. We also have these reversal events. So the barcode at the top is the polarity during the time, but every time over this time, and every time there's a polarity reversal, so the north pole switches to the south magnetic pole and so forth, there's a big drop in intensity almost every time you see that. Yeah, so we've got these two things, these sort of intensity and direction of the field changing over time. Okay, so a couple people have looked at this question of, if you look in the paleointensity record in particular, do you see anything unusual? Do you see anything interesting? What do you see? Do you see trends? Do you see a long secular trend in some direction or not? And the answer is no. Not nothing. It's just sort of scattered. So this one proposed, okay, maybe there's a jump here, although there's like no data. This one says the inner core could be 0.9 to 2 billion years old. That's a huge range of data. Again, there's still no data. And recently, this Nature paper did a more careful analysis of a more finely combed database, VADMs combined, and claimed to see some tower around 1.2, 1.3 billion years ago where there looks to be a jump in the field. Now, my first thought when I saw this plot was, well, the top data point is higher than the others, but at the same time, there's a whole lot of weak data maybe this isn't the best way to plot the data. Okay, so here's another way to look at the data. This is over the last 2 billion years now. We're going to zoom in on just the last 2 billion for the rest of this section. And each of these dots is a data point of median or VADM. Here's a histogram of the number of data points over that record, and a histogram of the intensities. And just recently, or maybe the last couple of years, a number of these data points, these are open circles, have been challenged by various people in the community as maybe not being representative of the primary remnants of the rock. So they're not preserving the ambient field of the time. There are a lot of ways that you could be confused by thinking it's a primary signal, but for now I'm going to use this open signal, open symbols. And this gray line here is a running average. There's another gray area you can't see of the average data intensity. So if we just focus on this black line here, it's the running average line. I don't really see any trends. I see a jog here, which could be just because there's a ton of well-preserved rocks, because there's a lot of volcanic activity at the time. I don't know. So we're going to use this as our comparison to the models at the end. Okay, so evolving numerical dynamos. So now I'm going to go take my simple 1D thermal history models and stitch them onto a much more complicated 3D magnetohydrodynamic dynamo model. So you're solving 4 coupled equations: Navier-Stokes, force balance, heat transfer, mass balance, and magnetic induction, all in a spherical shell. It's rotating. It's very low viscosity. It's all liquid. It's convecting. This is a modeled isosurfaces of magnetic field. And you can see inside the core, it's all mixed up like a ball of spaghetti, and outside it's this smooth potential field. It looks like a dipole field. And this is just as one of my simulations. So you can get a sense for how small scale and how dynamic. So this is like a couple thousand years of simulation. We're looking down into the equatorial plane, and the magnetic field is being contrast. So red being positive coming up, blue being negative going down. And the whole fluid is sort of processing to the west, but you get these large-scale vortices that actually transect all the way north to south through the core and concentrate magnetic field, get sloshed around for a while, and then dissipate. Okay? And this is the typical regime of dynamics that we see, at least in the models. The magnetic fields they produce are consistent with what we see in the present-day field. So we have some confidence that they're doing some of the physics right. But here's the biggest caveat, is that our parameter values are down here, and the Earth is way up here. So this is the measure of the rotation rate, the active number, 1 over the rotation rate omega. Our simulations are in this sort of 10 to the minus 3, 10 to the minus 5. And the Rayleigh number is a measure of the convection out of core. The Earth is up here. So we have this problem. We have no hope of getting here numerically because it's just too hard to resolve these physics at every grid scale for as long as you need to. Someone did a calculation, an optimistic calculation, and found that you have to run a model for 35 years, using tens of thousands of cores in parallel. So this is a horrible PhD project. Taking a message from this. So we've really got to build these scaling laws. We've got to understand the underlying physics. And recently people have shown that all along this track you find Earth-like magnetic field behavior. It's the criteria for Earth-like. And away from this scaling law, from this trajectory, this vector, you find non-Earth-like behavior. Okay, so we're building our confidence in our understanding of parameters. All right, so let's go back to the thermal history. I already showed you this plot. This is my preferred power for the core. This is the total in black. This line is the inner core boundary, which starts at 650. And then this is a sink, or source or sink, just to balance heat. And the blue line is the thermal cooling. Okay, so you sum them all up and you get the black line. So I'm going to use these 3 components as boundary conditions on my 3D Dynamo model. And this is the total driving power over 2 billion years. So I'm just going to model 2 billion years, which is a huge amount of time to model in a Dynamo model. So rather than doing something continuous, I broke it up into pieces. So I'm doing 25 stationary Dynamo models with fixed power. Hopefully get a stationary average field strength and direction and so forth. And then you'll see I have these little filled in circles with the inner core nucleates. So the present day inner core size is a completely full circle. Full circle. And this is what I get. And so this is completely different from that simple scaling law I showed you initially. What I find is the present day field is it's this so-called strong field dynamo, where the convection and the Lorentz force are acting against each other in about equal partition. And you create a strong field dynamo that's occasionally reversing. Magnetic field intensity is strong, but fluctuating a lot. Okay? And as you go back in time, you don't see much of a trend in intensity. And that's because you're sort of already saturated on the strong field branch. So even though the heat flow is decreasing a little bit, you don't see a trend until you hit this inner core nucleation event. And prior to that, the thermal heat flow is so weak that you're barely driving any magnetic field. In fact, it's a weak non-axial field. And by weak, I mean that the Lorentz force is weak, which means the magnetic field is weak, and the flow, just the kinematic flow, is controlling more of the dynamics, which means the dipole need not be axially aligned to the rotation axis as it is the strong field dynamo. It can be now recessing, doing all kinds of weird things. And if you look at the average latitude of the dipole in these models, time average latitude, my stable dipolar models, of course, are more or less stable, whereas in this weak field, there is no preferred orientation to the dipole. It just becomes random. And then if you go back even further, you actually switch back, so you jump back to the strong dipole model. And remember, the heat flow through this time is sort of decreasing secularly. So you the heat flow sort of passes through some threshold right around here, right around 1 billion years ago, where there's not enough heat to drive a strong field. There's not enough cooling rate to drive a strong field dynamo. There's not enough convection. And that's why you jump up to this strong field branch. And then prior to that, maybe there's too much convection, which actually puts you in a strong multipolar branch. Multipolar meaning the dipole is no longer the dominant field component. There's octopole, quadrupole, and other small-scale magnetic fields are equally energetic. So you get a weaker dipole moment because of that. And the intensity has also become very strange if the dipole component is not common. Okay, so you've basically got two branches, and that's what we're finding, is that you've got these two branches, weak field between 0.5 and a billion years ago, and then maybe before 1.6 billion.
So you can have strong field development.
Yes. This is really generated by having a high enough heat flow, or the boundary condition of the model is just flux the outer boundary of the inner boundary. So without the inner core, there is no inner boundary. It's just cooling from above. And there's enough cooling from above in this time to drive this strong field dynamo, at least temporarily. This is a couple snapshots of what the field looks like. Present day field, this is an equatorial temperature profile, and this is the time average surface magnetic field. It's just dipolar, that's the takeaway here. The inner core is large. You get these big thermal plumes coming off the inner core boundary, because that's where a lot of the power is being released in the present day. Go back right after the inner core nucleated at 580. Also have a dipolar model that's weak, the intensities are quite weak, and you get sort of a single plume or very, very few plumes coming off the inner core boundary. The dynamics changes a bit. And if you go back prior to the inner core nucleated around 680, you can see most of the temperature gradients are now concentrated to near the outer boundary, and that's because it's cooling from above at this point. And there's a passive boundary in the inner core boundary because I need to resolve I can't resolve the center of the Earth in my model. It's undefined in terms of latitude. So I have to put some kind of boundary down there. but it doesn't affect the dynamics. So I shrunk this down to different sizes and found that it didn't affect the dynamics. The time average surface field, of course, here is just non-dipolar at all. You take the time average at one point, it's different than the time average at a different point, and you usually don't recover a dipolar field, at least the time average is over here. These are movies. In case you want to see how this thing is evolving. So this is the non-dipolar field. You're looking at it from the side, and then the north polar, south polar view. And you can see that, the positive or negative field never really stabilizes at the pole, which is what you would expect for an axial dipole. Okay. And the present day is just for board. So this is the comparison between the two. This is my result I just showed you, and this is that paleo intensity record, except now I've binned it into 100 million year bins. So every 100 million years, I've got a single time average paleo intensity, and again, I'm doing a running average, this line here. And I wouldn't argue that these two look alike. I still don't. I don't see anything intense, right? I don't see any. The main problem here being there's like very little data in the near Proterozoic, which is exactly, maybe relatedly, where I expect there to be a weak field that doesn't have stable directions. Okay, so why is that? Is there something to that? Is this gap signature intercore nucleation? Yeah. Okay. So a couple slides on the implications. So here is now my sort of broad view takeaway of my history of the Dynamo over the last two and a half million years. It's sort of a cartoon form. So here's a sketch of intensity in black and reversal rate, or some proxy for reversal rate. My sort of hand-drawn cartoonish magnetic field lines. So we think that through most of the Phanerozoic, although there are fluctuations, supercon cycles, we've had a stable axial dipole most of the time. The dipole component's the dominant. The gas assumption holds. Through the near Proterozoic, my models predict sort of a weak field dynamo that's non-dipolar, non-axial, not stable at all. Intensity might be quite weak. You might interpret these as reversals because you see poles moving and popping up all over the place. And then prior to that, you recover back into the stable Mesoproterozoic stable axial dipole. And something I didn't mention yet is that there's another study that agrees with this perspective, looking at paleolarity ratios based on paleogeographic reconstructions and trying to recover superchron times from these polarity ratios. So we know that there are superchrons, the Cretaceous normal, the most recent one we see in the seafloor record, but we know there's a couple more in the Phanerozoic, and you see this in the polarity ratio data. There's a gap in a lot of the paleogeographic reconstructions, so we do not do a good polarity ratio study in the Neoproterozoic. Again, sort of interesting and frustrating. But in the Mesoproterozoic, we can play this game of looking for superchrons and polarity ratios. And we see sort of a couple superchrons, like 3 to 10 maybe, realistically, where the field does look more or less stable. So this sort of jives with my model using the energetics, that we sort of have this unstable, maybe unstable to stable period in the Mesoproterozoic. So I've hinted at this a couple times, but I just want to show what I mean when I say paleogeography. So these ancient plate reconstructions, how we know where the plates were and that there were supercontinents at all, are informed by the paleolatitude from paleomagnetism. But those paleolatitudes typically assume a global axial dipole. So you get some local rock, you don't know where it was, you measure the magnetic field, and you assume the Earth at the time had a global axial dipole. And then that allows you to locate your continent in latitude. It's not longitude, but in latitude. And you can do this. You do this for as many samples as you get your hands on. Now, this apparent polar wander, where you see where it looks like magnetic field when the rock is moving could be caused by at least three things, probably more. It could be the continent moving in the presence of a global axial dipole. It could be the rotation of the entire lithosphere and the entire Earth. This is called true polar wandering, one of the most extreme claims. And the other option is that the magnetic field itself is just wandering. So sometimes it looks like the models favor that case, right? But the field itself is not axial dipole. Okay, so it turns out that the near Proterozoic is full of these really weird plate reconstructions, paleogeographies. So here I'm listing just the last 12 years of sort of a couple that I can get my hands on, from 8-10 million years ago all the way up to the end of the Cambrian boundary. And they almost always find something a little bit weird about the paleogeography. There's often plates that look like they're swinging across the surface of the Earth really quickly with speeds 50 centimeters per year or something that are just crazy, like 10 times the fast plate speeds today. People don't think that those are plate speeds, right? People think that it's either extreme polar wander. People propose an equatorial dipole field to measure particularly these bitter springs data. And then more recently, people have said that, well, there's actually a bunch of reversals. And if you assume something about the sediment rate or whatever, the reversal rate looks much faster than presently. So maybe we had a hyperactive dynamo, which I would say you could be interpreting a non-axial dipole. It's just not a line, so it looks like it's reversing. If you're looking at octopolar components coming and going, they look like reversal dipole. So the main takeaway here for me, and this is sort of sketchy still at this point, is that if the non-axial dipole field, or the non-dipolar fields were significant in the Proterozoic, as my model predicts, some of the paleolatitudes inferred by these studies could be unreliable. Okay, well, what do we get about that? Well, it turns out that reconstructing continents at the time, Rodinia, is very unsettled. So here's a paper from Dave Evans in 2013 showing 4 different options for the locations of the continents about 800 million years ago. And a lot of the uncertainty comes from the magnetic poles just being scattered. And they're consistent with the continent being here or there, or have their different favorite locations and reconstructions. So that's very unsettled. And the last implication I want to touch on very lightly is the idea of these Snowball Earth events, which are still highly controversial. I don't want to claim that these are accepted by everyone in the community, but there are these what look like there are these carbon-13 excursions, which you're seeing here, the data point here, that are co-eval with these carbonate and dimectite layers. People have interpreted it as contacts between glaciers and rocks, and inferred that there's a Sturtian glaciation that's actually quite long, unimaginably long, actually, 50 million years long, and then maybe a shorter Marinellan one and so forth. But a lot of the paleolatitudes, for example, this plot, come from the Paleomag. Okay, so people are putting a continent maybe at low latitude based on the Paleomag and saying, oh look, there's ice. Whereas latitude could be off, right? And so maybe you're just getting a glaciation at higher latitude. So here's the full span of paleolatitudes, right, with glacial deposits found. And it spans the whole range. So I don't know. There's a lot going on here, obviously, but the underlying assumption that the magnetic field is just this boring, globally actually dipole field that we can use as a framework for disentangling all of this, I think is overly simplistic, particularly right around the time we think the unicorn nucleator, which is in this time frame. Okay. This is the extent of my knowledge about these things. So here are a number of the conclusions that I pointed out. That to solve the thermomagnetic paradoxes, one way to do it is to bury about 3 terawatts of heat somewhere in the deep interior. The way I did it was in the core, but you can put it somewhere else. This solution, I should say, is not unique. There's other ways, there's other knobs you can turn to get a similar solution. My evolving numerical dynamos predict a weak field, non-dipolar field in the near protozoa. And this was sort of reproduced by a second paper by a completely different group that came out about a year after mine. And they find bistable weak fields in the near protozoa. So there's still some work to be done. There's only 2 studies now, I guess they've done this. But there's some support also for this numerically. There's a whole list of anomalous paleointensities. I should say there are plenty of normal paleointensities, paleodirection in particular, in the near protozoa, but there's a lot of anomalies. Right? So maybe the field is stable at times, unstable at times. There are these snowball events that are proposed during this time, but some of those paleolatitudes could be a little bit misleading if the field is non-net at the time. And last, there have been a couple ideas thrown out there, papers, that some of the evolutionary radiations, biological radiations, are correlated with changes in the magnetic field. So maybe there's also a connection between the inner core nucleated, creating a shield that then allowed became greater radiation. That's the craziest. But I just wanted to mention it because it's totally connected to the story. Okay, I'll stop there and take your questions.
Do we see any turnover of early life when the change from the stable Mesoproterozoic to the unstable Proterozoic?
I don't know. That's a good question. Yeah, sort of paleontologist answer. A lot of the change happened in late Proterozoic.
Yeah, it's about 580 in your beginning of the inner core formation.
Yeah, my inner core nucleate's around 650 with this particular model, which is a huge amount of uncertainty. And the field doesn't recover until maybe 100 million years or so after that. Like a couple Dynamo models after that, you get a strong field.
Which is like just about co-equal with the above explosion.
Yeah, pretty close. But there's a couple, there's some significant, changing the core radioactivity or the core conductivity or the mantle cooling rate. Changing these things by a few percent will change the age of the inner core by 50 million years, 100 million years. You should take the timing all with a grain of salt. And the Dynamo models are also, because we're so far from parameter space from the Earth, we should be doing models as close as we can. So we can always refine our Dynamo models. And that might give us a slightly different magnetic field response to that thermal history too. Yeah.
So, can you explain physics, not chemistry, but the physics behind letting protozoic for parameterization convection?
Why beta value might be 0?
The core levels.
Yeah. Can I explain the physics? Well, my understanding is the heat loss can be related to the thermal boundary layer thickness, the crustal lithospheric thickness, if you want. And in a hotter mantle, create a thicker crust that's harder to bend and conduct. And so it's actually harder to cool the mantle.
What about the latest? I think Solomon and others have suggested in a hot Earth, mantle crystals get larger. You can anneal grain damage, and it's counterintuitive, so that the hotter it gets, the stiffer it gets.
Yes, there are ideas, grain damage ideas, that you can't preserve weak zones when the atmosphere is hot, and it makes it harder. Just that's another one. I mean, my caveat to these are always, from a thermodynamic point of view, they're mechanical arguments, whereas there's a bunch of heat beneath the crust at the time, Archean, Archean, and it wants to get out. And you're also doing a bunch of melting, right? You're applying a bunch of melting by these arguments. And I just wonder what's going on. Is that melt erupting? Are you having a lot more eruptions or not? And are you maybe losing the same amount of heat that you're trapping from stiffening the lithosphere just by eruption? Right, so that's, I don't know the answer to that, but it's not really big considered.
So even in a thick lithosphere, you would have the same heat flow just because it's advective from melting.
Yeah, instead of conducting the heat, you're just dumping a bunch of salt in the crust. The rate is still controlled by the upwelling solid, right?
Mm-hmm.
Which is controlling the melting rate. But you're dumping it on the surface, like, instead of relying on conduction through that crust. Yeah.
If you look at observations, this is what we know about what's going on in other planets and in our solar system, and we see different fields out there. Have you thought about how that might relate to what you're
Well, the Dynamo models can produce all kinds of fields, and they're very sensitive to where you are in parameter space. So my sequence of 25 dynamos was anchored in the present day. Right? I made sure that my present day model reproduced the Earth to the best that I could, and then used the thermal history to predict everything else. So for these other planets, their heat flow could be whatever. You know, their dynamo region thickness can be whatever it is, and that can play a huge role on the magnetic field morphology. So, for example, to kick the Earth into a multipolar regime, you just need to increase the heat flow today. Kick it into a frequently reversing regime, the same thing. Just increase the heat flow temporarily, and that'll do it. Vice versa. So these multipolar dynamos could just be cooling more quickly. It could be the AT-vats could be much smaller, so the thermal convection is much stronger.
Following up on what Carl just said, so do you think that maybe Venus at the present time could just be in kind of a napping quiet stage?
Yeah, my thermal history models for Venus show, if you assume a stagnant lid, that Venus doesn't have an inner core, and that the thermal dynamo on Venus shut down after a billion years or two. So today the core is just not convective. So Venus' interior is actually hotter than Earth's.
But there's no convection.
Right, because to drive the convection, you need to be drawing heat out via heat flow. If you're not cooling the interior, you're not driving convection. So it's a little counterintuitive.
Okay, we're gonna, oh,
Yeah,
sorry.
So what do you think is the threshold dynamo action required to have a dipole field? Because if you try to do it experimentally, there's really no way of figuring out if you have a dipole field from directions once you scatter the contents in the neoprotozoic. So the question is, in the models in the neoprotozoic, how low can you go and still have a dipole field? You essentially imply that there's no field, or just
No, there is a field.
multipole field?
That was a time averaged intensity field on the branch.
But is that a multipole field?
It's a multipolar.
Why? At what level can you still maintain a dipole field?
Because it's multipolar because in those weak field branch, the magnetic field is so weak that the flow doesn't feel the magnetic field. That's the Lorentz force. Okay? So if the flow, the convection, these vortices that I showed you, are not affected by the magnetic field itself, then the dipole components are not going to be aligned with rotation. The dipole components are being sloshed around by the convection. And you just don't get an axial dipole. You can have a dipole that's just precessing maybe, or equatorial, or just a mixture. But in these models, actually, I find the quadrupole and octupole are similar power to the dipole in that case.
But not along the rotation axis. That becomes
Right.
a problem.
Well, they're just not aligned for a long enough time, you know, if you wanted to get a direct